Alright, so in this video we are going to talk about relative reactivities of carboxylic acid derivatives. Now, before we go any further with a question like this, then the one thing you want to be able to do is to actually identify what is what, okay? And you can see, hopefully, that when you look at the left-hand part of each molecule from this bond back, all the molecules look exactly the same. So really, the only thing that differentiates them is essentially the group sticking out to the right-hand side. Okay. We've seen all these before, with the exception of this. We didn't do any naming of thioesters, but thioester is essentially the same thing as an ester, except with a sulfur where the oxygen is. Like I said, we're not going to worry about naming, but we will take them into account when we look at relative reactivities, which is what we'll do now. So, as you can imagine, this group, or the identity of this group, is essentially the most important thing that determines how reactive a molecule like this is. And if you've watched the previous video, you've seen that nucleophilic acyl substitutions are simply a nucleophile coming in here, kicking electrons up onto the oxygen, which then kicks them back down again and kicks out the leaving group. So what this really comes down to is, out of these 5 underlying groups, which is the best leaving group? Okay, that's what it all comes down to. So we have this chloride, this NH2. Now the only way that we're going to figure out which is the best leaving group is to actually draw them out as they would be as leaving groups. Now you know Cl comes off as Cl minus. So there's one leaving group. SCH3, if the electrons come from here onto the sulfur, would give you SCH3 minus. Okay. OCH3 would give you a leaving group that would look like OCH3 minus. With the amine, with the amide, you get a leaving group that looks like NH2 minus. And then with the last guy, the anhydride, when that group comes off, you get something that looks like this. The oxygen's a little big, but still. So what we're looking for is which is the best leaving group, and so what that comes down to is which of these is the most stable. Alright? Well, you'll probably have a pretty good idea about which of the 5 is most reactive in the first place. And you probably all guess that the acid chloride is the most reactive of the bunch, and it is. So that says that chloride's the best leaving group, so therefore Cl minus must be the most stable of our leaving groups. Okay? So therefore most stable. Alright. So what we're going to do here then is to figure out an order for all the others. Okay, Cl minus is the most stable, so that means that the acid chloride A is going to be most acidic. A is most acidic. Okay, we were talking about, I'm sorry, I just had to pause the video and start it up again, so if I seem like I'm starting over again, I apologize. Okay, we talked about that the chloride ion was the most stable leaving group, therefore the acid chloride was the most reactive. So let's look at the others. Let's look at, say, for example, SCH3 minus versus OCH3 minus. You can see those two are very, very similar. All right. In fact, let's compare the NH2 as well. If you look at the relative sizes of these, N, O, and S, sulfur is the biggest. Now, the bigger the atom is, the more easily it can accept electrons, or the more easily it can spread electron density around itself. So what that means is, comparing SCH3 to OCH3, the sulfur, because it's bigger, means SCH3 minus is slightly more stable, and so therefore SCH3 minus is a better leaving group. Alright, so I'm going to do a little ranking order here. 1 meaning most acidic, because that's the best leaving group, and therefore that means, let's see, okay, sorry again. That means that the SCH3 minus is more stable than OCH3 minus. However, we've got to take this guy into account as well. If you look in figure 16.2 in your textbook, this is kind of a useful table. It gives you a graph or a little diagram that shows you which is more reactive and what can be used to make whatever else. And what it shows is that the acid chlorides are the most acidic, and the most reactive, I should say, and then the anhydrides, are the second most reactive. Therefore, that says that this guy here, this is the second best leaving group. Now, when you compare oxygen to oxygen, it looks like they should be the same, but there's one reason why this is more stable. In fact, it's also more stable than the SCH3-. You remember the 1, 2, 3 relationship of the charge and the double bond? What's that one word beginning with R that should be screaming out at you? Of course, that's resonance. You can actually take this O-. Oops, I know there's some pretty crappy arrows there. Let me try those again. Let me draw that whole thing out again, I'm sorry. Okay, talk amongst yourselves. So, did you see that movie last night? Great. What the hell are you talking about? Okay, so here's our O- again. I'm just trying to show some resonance arrows, so that goes in there, picks those electrons up onto the oxygen, and would give you something that would look kind of like this. So what that means is you can spread that charge around those two atoms, and that makes this leaving group the second most stable. Now let's get back to these two. We said before that if everything else is the same, sulfur is bigger than oxygen, and so therefore the sulfur can accommodate the charge easier than the oxygen can. So that means the SCH3- is more stable than OCH3-. But we haven't talked about this guy yet. Now, when you look at these 5 functional groups, you'll see, or hopefully you should see, that one of them is actually something that makes up a large portion of our bodies, and that is the amide. Amide bonds, or peptide bonds, make up virtually all of our proteins and enzymes and things present in our body. So what do you think that says about this group in terms of stability? Well, you'd be right if you said, well, it must be very, very stable. And if that means if it's very, very stable, then what do you think that says about this as a leaving group, this NH2-? Well, you'd be right if you said, well, if that's really stable, then NH2- must not want to come off at all, so it must be a really crap leaving group. And it is. If we compare relative sizes again, sulfur is the biggest of the 3 here, oxygen's next biggest, nitrogen's the smallest. Nitrogen is not happy at all bearing this charge, so therefore that means that doesn't want to come off. So what that means is an overall order here is so. Acid chlorides are most reactive, and that means you can use an acid chloride to make any one of these other 4 molecules, because chloride's the best leaving group. Acid anhydrides are the next best leaving group, which means you can use an anhydride to make any one of these 3. Can't use it to make this because chloride's a better leaving group than this. SCH3- is the next best leaving group, so that means you can use a thioester to make an amide or an ester, but nothing else, because again, these 2 leaving groups are better than this one. And then for the ester, the only thing you can make from an ester is an amide, and then an amide, well, what do you think you can make from an amide? Well, using a nucleophilic acyl substitution, you can make nothing from an amide. We'll see in a later video you can do something particular with it, but we're not going to worry about that now. So there's a simple order of reactivity for acid carboxylic acid derivatives, and I hope it makes sense. Thank you.